Now we'll see how this goes. I have my sleeping daughter right here on my lap. I'll even prove it by taking a picture of us. She's pretty cute. Oh, but you probably don't care that much. So let's get back to Hess's Law. Something completely entertaining that I'm sure you're at home happy to be watching. This drawing is supposed to show an elevator on the first floor going up to the second floor. At the same time, there's steps that can go up. What Hess's Law is saying, and we can apply it to walking or riding an elevator, is that your change in energy is independent, meaning it doesn't matter whether you go up the stairs or you go up the elevator. The change in energy is the same, because it's simply how far you are from here. So if you fell from there to there, you would feel the same pain if you fell from there to there, whether you rode the elevator to get up there or the stairs. So the way that we apply this to reactions is that sometimes a reaction doesn't just go A to B. It has A with some steps that go to B. If we don't know the change in energy here, but we do know the change of energy of each step, we just find the sum of the steps, and that'll equal my change in energy. That's Hess's Law. So the way that we can apply that will be on the next slide. And it's a question where you're given a reaction and you're given its steps and then asked to solve for the overall reaction with the steps. All right, so this is a typical type of problem you'll see when you deal with Hess's Law. And I had a little misprint here, so that's why that looks goofy, but don't worry about it. All right, so we have this reaction given to us. This liquid plus oxygen goes to CO2 plus sulfur dioxide. This would be carbon disulfide, in case anyone cares, which is really a dangerous and nasty liquid. So it doesn't surprise me they don't necessarily know the overall change in enthalpy, because it's not something people deal with very often. All right, so we don't know the change in enthalpy. That's a question mark. So, all right, got interrupted, but so we do not know the change in enthalpy here, but we know these are three reactions with known enthalpies over here. And if we can arrange these in the right order so that we have the reactants on the correct side and the products on the right side, and we can adjust these enthalpies, like their signs or their values, in the same way that we rearrange this, then we can just add all these enthalpies up and we'll get what we call the net enthalpy, or the change in energy for the overall reaction. So, all right, so let's go ahead and look. What I generally like to do is find things other than oxygen to start with, because oxygen generally, and if you look down here, it's in two places. So I prefer personally to start somewhere else. So I look here, I need to make sure that these reactions, because we're going to add these reactions together, I need this carbon disulfide liquid on the left side. If you look over here, it's on the right side, and it has a value of 1 right here. And it's already balanced, so if I see that it's on the right and I need it on the left, I have to rewrite this equation for the reverse reaction. I'm not going to do that because I don't necessarily care about the reaction, I care about the enthalpy of reaction. So if this reaction in the forward was positive 87.9, in the reverse it's going to be negative 87.9. so that takes care of that. It's now on the left side. Now I'll leave this till the end. The next one I'm going to go to is the 2SO2. So I come down here and I can see that I have SO2 on the right side, and I want it on the right side, so that's good. But I need 2 of it. SO2 is in no other of these reactions. So what I have to do is double everything in this reaction. That gives me 2S plus 2O2 goes to 2SO2. As part of doubling that, I now must take the enthalpy and multiply it by 2 as well. Alright, now, finally, that takes care of that. I'm going to look at CO2. I need it on the right side, and I only want one of them. I come down here, and I can see it's already on the right side, and I only have one of them. So I'm going to leave this one the same. So, mathematically, what I'm going to do, and this is, I know it's kind of ugly, but just kind of go with me here. Mathematically, I'm going to take this value. I'm going to take 2 times that value. And I'm going to take negative 87.9. I'm going to add them all together. Alright, so I rewrote this. And I added up all the values. And I get a total of negative 1074.7 kilojoules. Yep, looks like it was kilojoules. Alright, so that would be the overall heat of reaction, or enthalpy change, whichever way you want to call it, for this reaction I had right down here. Alright, we use that applying Hess's law, which says that the steps add to the whole. Alright, well, let's go ahead and do one more. The next one I'm going to show you the question. I want you to pause it and give it your own shot first. Okay, go ahead and give this a shot. What we're trying to do is calculate the delta H for this reaction right here using these reactions right here. So these are the steps. This is the total. So go ahead and give that a pause and solve for delta H. I should mention quickly, there's no reason why this says kilojoules per mole and this one do not. They're all kilojoules per mole. Alright, it's a completely different day. Life seems to always get in the way, so let's just review how to do this. Well, what we're doing in this problem, we don't need to obviously review because you just watched this. Alright, so we're solving for this reaction down here using these reactions up top. Alright, so if I look down here, I want to find SiH4 on the left. As you can see here, it's on the right. So I'm going to take and rewrite this equation. SiH4 goes to Si plus 2H2. If I switch this, that means that this delta H must really be negative 34. Alright, I don't look to see to have to manipulate it mathematically because that's a 1 and that's a 1. So I just had to write the reverse reaction. Alright, let me get rid of that, some of that. Alright. Now, as I look down here, I have SiO2 on the right. It's on the right here. They're both 1 and 1. So I'm going to keep this the same. And I have 2H2 on the right. I have only 1 H2 over here on the right. Alright, and that can't happen. So I better double this value. And that'll make sense because I have the 2H2 to cancel this 2H2 out. I now take 2 times a half, so I have 1O2 plus 1O2 makes the 2O2. And my waters are now 2 waters to take care of that water. So now I have all these taken care of. Now, since I doubled this here, I'm going to have to double this value here. And then do the math. So I have negative 34 plus negative 911 plus negative 482 if you multiply that out. I don't have my calculator handy anymore, but that's some sort of number. Okay. All right, we'll wrap that up there. The homework problems that are like this, I think, are in the 60s, because I don't have my book with me either. Go ahead and give those a try, and good luck.